Okay, let's start today with the Fermat's theorem. Okay, so this is a necessary condition to find minima and maxima. Okay, so I start from here. Okay, so we have, so you want to find min-max points of a function. Okay, so let us draw a figure. So this is the picture. So first let us concentrate on what happens at the maximum case. So let us exaggerate and give a typical nice figure like this. So this is our function y equals f of x, and this is the graph. So here is the point x sub 0. Then I push x sub 0 a little bit, x sub 0 plus delta x in the figure. So this is delta x positive. Okay. If delta x is negative, I again write x sub 0 plus delta x sub 0 plus delta x, but here delta x is negative. Okay. Now we assume that, so we assume f is differentiable. That is, f prime x exists at every point. We are interested only at x sub 0, but in most cases, f prime will exist on an interval, and we'll check these things. So at this point, we have a maximum, and the tangent line is horizontal there, as we observe. Okay, so this is the tangent line. Tangent line here is horizontal. Okay. And we know that if the derivative exists, if the tangent line exists, it is approximated by secant lines. And these are the two secant lines that we are going to consider. Okay, so let's make this a little bit like this. Okay, so these secant lines, approximate the tangent line from left and right. Okay. So this is the geometric situation. Now let's pass to the algebraic calculations. Okay. In the algebraic calculations, what we want to say is that the slope of this thing approaches to the slope of the tangent line. Okay. And the slope of this approaches to the slope of the tangent line. This approaches from the left. This approaches from the right. F prime exists, so these right and left limits must be the same. Okay, so algebra. Now algebra. Okay, so f prime x sub 0 exists. It is given by limit delta x goes to 0 of f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. Okay, now this is the slope of the tangent line here. From the figure, we expect that the slope will be 0. Okay, but of course, we have to check if algebra agrees with this or not. Now this one is unrestricted limit. So we look at the right and left limits. Since the limit exists, right and left limits exist and are the same. So I calculate limit delta x goes to 0 from the right. So this one, f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. And also, it must be equal to the other limit. Delta x goes to 0 from the left, this limit. Okay, f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. When delta x is positive, this is the picture. Okay, so we are assuming here that this is maximum. Okay, let f of x sub 0 be larger than or equal to f of x around x sub 0. Okay, so that is max point. Okay, so now we translated the picture fully to algebra. So now the figure may not be as nice as this. The figure can be very complicated. Okay, so and believe me, there are very interesting examples where you have no idea what the curve is doing. Your only choice is to rely at these calculations. Okay, so let us look at here. So this is equal to limit delta x goes to 0 from the right. F of x is larger than f of x sub 0 plus delta x. Okay, f of x is maximum. F of x sub 0 is maximum number. So this is negative. Okay, so this is negative. Delta x is positive. That's what we are taking. Positive. So the whole thing is negative. We are taking the limit of something negative. Okay, so it cannot be positive. So it can be less than or equal to 0. Okay, so we play the same game here. So this is limit delta x goes to 0 from the left. And the same situation here. F of x sub 0 is maximum, so this is negative. Divided by delta x. This time delta x is negative. So the whole thing is positive. And you are taking the limit of something positive. It cannot be negative, so it is larger than or equal to 0. Okay, so what we found is this one. So we found from here f of f prime x sub 0 is less than or equal to 0, but also larger than or equal to 0. Okay, so from these things. Therefore, our geometric expectation is confirmed by the algebraic method. F prime x sub 0 is 0. Okay, so this is this is Fermat's theorem. So we just proved Fermat's theorem. Okay, so f differentiable on an interval has mean or max at x sub 0, then f prime x sub 0 equals 0. Okay, so you will notice that I proved this only for maximum, but here I'm mentioning this also for minimum. When this point is minimum, that point is minimum, then the only thing that will change is this part here. Okay? If f x sub 0 is minimum, then this is positive. So this will be positive, positive. But the denominator, the sign of the denominator changes. So one of them will be non-negative, one of them will be non-positive. And we'll have again this situation. Okay? The sign of the numerator remains the same. The sign of the denominator changes because of delta. Delta can move in this direction or in that direction. So the same argument will also give me the setup in minimum case. And in both cases, the derivative will be 0. Okay? So that's Fermat's theorem. Okay, so we also noticed through some examples that min-max can occur at a point where f prime does not exist. Okay, so these are points where there is no tangent. Okay, so we call them singular points. So our example was this. So let us look at, so we can have something like this. Okay, so here the derivative is 0. Okay, so let's cut it over here. But here we have maximum. The derivative will be 0 here. But such a thing can exist. Two paths can join at that point, and this friendship is not smooth. Okay, one wants to go in one direction, the other one goes in the other direction. Okay, so there the derivative does not exist, but you see that such things can occur, and at that point we have a minimum. Okay, so we define critical points. Critical points as points in the interval where either f prime does not exist or it exists and it is equal to 0. Okay? So you see that these are candidates for minima and maxima. At a critical point, we can have local minima, local maxima. We can have global minima, maxima. We can also have inflection points. Okay? So for example, y equals x cubed does not have a minima and maxima on the real line, but at the origin, the derivative is 0. So 0 is a critical point. Okay? So we don't care. We just call them critical points. Our hope is that when we work on a closed and bounded interval, there will be finitely many critical points, and we will check all of them one by one, and one of them is the maximum point. Okay? So how to find min-max points of f on a closed and bounded interval. Okay, so when f is differentiable on AB except at finitely many points. Okay, so for example, in this case, I can take my interval like this. This can be A, this can be B. So here you see the derivative is 0. This is a candidate, this is a candidate. The derivative does not exist. Okay. So first find the critical points. So critical points means you look at the derivative of f. If there is some 0 division, or if there is some, if maybe the function is given as a split function, at the point where the two functions join, you have to check whether the right limit and left limit of derivative exist and agree. If not, that's a critical point. Okay, so first we find the points where the derivative does not exist. It's generally easy. You just look at if you have one formula, you look at the denominator. If there's a denominator, 0 division is a bad point. Then you find the points where the derivative is 0. And the important thing is that you only take those critical points inside AB. First, find the critical points in AB. Okay? For example, it's clear that in this figure, probably the function I write here is an upside down parabola. It goes down like this. Okay, or maybe it's a cubic, it goes down like this, turns out like this. There is another point here where the derivative is 0. It is not my critical point for this setup. My setup is the function together with the interval. Okay, so this is one of the points where you want to be careful. F on, so this is my setup, our setup. Okay, so in particular, when there is a word problem, for example, you want to find the best route to carry something from some point to some other point, and there are differences in the cost along the way. Okay, so you set up a function to give your cost to your cost when you carry something from here to here. But that makes sense for certain values of the parameter. Okay, most of the time your function will tell you that if you go this way and this way, you spend a lot of money. But of course we know that. Okay, so you restrict this only at a meaningful part, and then when you take the derivative will be 0 somewhere. Also somewhere outside the interval. Okay, you don't check what's happening there. You only find the critical points in AB. Evaluate F at these points. Okay. Also check endpoints. Okay, so you have F of A and F of B. Okay, so you see in this picture that if I choose a little bit here, this thing goes down, and this point will be minimum for this function. This function won't be minimum anymore. Okay, so the endpoints this also has a say, have a say on where the function is going to have its minimum and maximum. At these. Okay, so let me, in order to make this a box by itself, evaluate F at critical points. At critical points in AB. Okay. And you also have F of A, F of B. Okay, so max of these numbers is max of F on AB, and mean of them is mean of F on AB. So this is the procedure to find minima and maxima of a function on a critical point. Of course, the question is, what if the minima and maxima does not exist? Okay, so you see that this procedure is mechanical. You start with F on an interval, you take the derivative, equate that to 0, find where the derivative is not defined, evaluate F at those points, 2 more numbers, find the minima and maxima. Okay, so these will always give you 2 points, 2 numbers as minima and maxima. But min and maxima exist because every differentiable function is continuous. Okay. Every differentiable function is continuous. Every continuous function, a continuous function on A, B always has mean and max. Okay, so that's that's the reason why we examined slightly briefly continuous functions. We didn't prove this, but we mentioned that minima and maxima exist for continuous function. Okay, so that again, that's a deep result. Goes to properties of real numbers, that given any collection of real numbers, there's a supremum and infimum. Okay, this corresponds to the axiom that in real numbers there are no holes. For example, in rational numbers there are holes. Okay, so if I start a differentiable function on a closed and bounded set, then it is guaranteed that a minimum and maximum exist on that closed and bounded set. And this is the way I find the minima and maxima. Okay, let's see Okay, so here. Okay, let's do some examples. So let's do an example. So let's say problems. So let us assume that our function is x squared. So it's a simple function, but I'll emphasize the importance of the endpoints, okay? Because this is something that you tend to forget in the exam, because it's very easy to check the endpoints. You forget that. You think that it is not important, and then you are surprised that so many points are taken off from your correct solution, okay? So it's not a correct solution if you miss the endpoints, and this is what we will do. We will consider this function on 2 or 3 different intervals, and you'll see that the endpoint decides what's happening. Okay? Okay, let's say on -1, 2. Okay? So the graph is something like this. Okay? So this is 1, this is 2. So the point here is 1, 1. The point here is 2, 4. And this is the point that we are also interested. This is 0, 0, x, y. Okay, so here f prime x is equal to 2x. The derivative is defined everywhere. So in the critical points, I will not be looking at points where the derivative is not defined. Okay, so f prime equals 0 when x equals 0. This is a critical point inside my interval. Okay. So I evaluate f of 0 and I get 0. Then I look at endpoints. Okay, so I calculate f of -1. Okay, so this is -1. F of -1 is 1. F of 2 is 4. Okay, so the rule says that I consider only these. Okay, so minimum of f on -1, 2 is 0, and maximum of f on -1, 2 is 4. Okay. Let us look at the same function on a different interval. F of x equals x squared, say 1, 2, or 1, 3. Okay, so now the picture is something like this. So this goes on like this. Okay, y, x. So this is 1. This is 3. So this point is 1, 1. This point is 3, 9. Okay, so now I look at f prime x. This is equal to 2x. F prime equals 0. F prime equals 0 when x equals 0, but 0 is not in the interval, not in 1, 3. So I don't evaluate f there. Okay, endpoints. F of 1 is 1. F of 3 is 9. So these are the only numbers I consider. And from here, I get that minimum of f on 1, 3 is 1. Maximum of f on 1, 3 is 9. Okay, very simple example, but this is something that happens also with complicated functions. You have to know what the function is doing at the endpoints. If the interval is not bounded or closed, then minima and maxima may not exist. So for example, in this example, if I didn't include 3, there is no maximum for this function. Okay, the function never takes the value 9. Okay, let me also make this just another example. Again, f of x equals x squared on 1, 3. Okay, and the last point is not included. Now, this is not a closed and bounded set, so the theory does not guarantee us anything. Okay, so it is possible that the function has minimum and maximum here, but the theory does not claim anything. You have to examine the function separately. So in this case, it doesn't have a maximum because the picture is something like this. It starts from here, and it doesn't take this value. This is 3. This is 1. Okay. So we examined everything here, except that here f does not take the value 9 because f is not defined on x equals 3. Okay? So here, minimum f on 1, 3 is 1. Max does not exist. Okay, x squared is obviously defined at x equals 3, but here we are not studying x squared. Somehow you modeled the thing that you are working on, and it turned out that this function models your theory. Whatever you are working on, this function is a model for it. Okay? So now, in your case, x equals 3 does not make sense. Okay, so you cannot say that my function will take the maximum value 9. Your function will never take 9. It will, in this particular case, we check that it approaches 9. So this is the situation where you invent a new word. You say the supremum of the values of my function is 9. Okay, so that's why you summarize this whole thing into one word. That's supremum. Of course, it is possible that if you have a different function here, the function has maxima and minima. Okay, so for example, we have such a function. Okay, so it starts at here, it goes like this, and now it doesn't take this 3, 1, and suppose this is, I don't know, this is 11, y x, y equals f of x. Okay, so some function. The function never takes this number. Okay, so suppose this is 7, this is, I don't know, 2. Okay, so this is our function. So in this case, you find the critical point. So suppose the critical point is here. Okay, so 1.9. Okay, so here, f prime 1.9 equals 0. Okay, so 1.9 is a critical point. Therefore, you calculate f of 1.9. And in this picture, you find that it is 11. Okay, so endpoints, you have only one endpoint, 2. F of 1 equals 2. But is this minimum? Okay, in this case, you have to also check limit x goes to 3 from below here, f of x. And that is equal to, in this case, 7. Okay, now you look at these things and you say minimum is 2, maximum is 11. Okay, so let's do a similar example here with this function, 5. Suppose now you change your setup, you model your situation, and it becomes something like this. And it doesn't take. So this is again, okay, let's say this is 5 now. Okay, so this is 5x, y. This is your new function, f of x. So at this point, let's say this is 3 now. It is 15. And this is 2, I don't know, 4. And this one is minus 3. Okay, so this is our function. We look at the derivative. So f prime 3 equals 0. So you calculate f of 3. It turns out that this is 15. Endpoint behavior, endpoints, f of 2 equals 4. F of 5 is not defined. So you look at limit as x goes to 5 from below f of x. In the picture, it is equal to minus 3. So this is less than this. So this function has no minimum, okay? No minimum. And max is 15 obtained at x equals 3, okay? So we have a machine, but the machine of this taking the derivative, equating at 0, also evaluating at critical points, endpoints, that's a machine, but it's just like a car. It doesn't take you anywhere. You have to drive the car. Okay, so in these cases, you see that you keep this machine. Wherever necessary, you apply the machine, and then you pull it back, and you again check what you have to do next. Okay, so another example would be the domain is unbounded. Okay, so let's see. Let's erase this one. It's easier to erase. Okay, so this is, what's the number there? 5, 6. F of x equals 1 over 1 plus x squared. So x is on R. So the domain is not closed and bounded. Okay, so we call R closed, but it is not bounded. So again, the theory does not guarantee that there exist a minima and maxima. You have to use your own judgment. But since this is a minima maxima problem, we immediately start with taking the derivative. It will be useful anyway. So this is minus 2x 1 plus x squared minus 2, right? Correct derivative? Okay. So this is equal to 0 only at x equals 0. This is inside the domain. So I'll calculate f of 0. This is equal to 1. So this is one of the numbers that I'll use. Then I have to consider endpoints. The endpoints are at infinity. So I look at endpoints. So I look at limit as x goes to plus infinity of f of x. Okay, so it is 0. I look at the other endpoint, x goes to minus infinity of f of x. This is again equal to 0. Okay. But the function is never 0. It's always strictly greater than 0. Okay, so the graph is something like this. So we again sketch a graph to convince ourselves of what is happening. It is something like this. X, y. Y equals 1 over 1 plus x squared. X is negative or positive. The function takes the same value. At x equals 0, the function takes the value 1. Okay, so the maximum of the function is 1, but the minimum of the function does not exist. No matter which number, which positive number you consider as the minimum, the function becomes smaller than that. Okay, so maximum of f on R is 1, attained at x equals 0. F has no minimum on R. Okay, so if you want to use the terminology here, infimum of f, or maybe I write it in words, infimum of f on R is 0. Okay, because you see 0 is a significant number here. That's the function approaches to 0. If you take any other number here, there's always a distance between this number and the possible values of f. Okay, so 0 is the only number that between 0 and any number, the function enters that interval. Okay, so that's one way of technically defining infimum, but this is where you invent this notion. You see that 0 has some significance here. Okay? So instead of describing this with your arms and figures, etc., you summarize all of this by the word infimum. So similarly, it can be defined as, so similarly. Now the derivative of this, I'll leave it to you, minus 1 over x squared, x. Okay, so this is a split function. Do we have time? Okay, so let's do this function also. This inevitably shows up somewhere. Okay, so now you have to wake up and take the e to the minus 1 over x squared if x is different than 0, and 0 if x equals 0. Okay, so what is f prime x? F prime x. Since this is exponential, I'll have minus 1 over x squared here. Okay, now what is the derivative of the other thing? What's the derivative of this guy? Now you have to take the derivative of this, right? Minus 1 over x squared derivative. So what is it? Minus 1 over x squared. You are going to have a midterm this weekend. If you don't know how to take derivatives, you are in big trouble. So what's the derivative of this? Okay, so this is 1 over x squared is x to the power minus 2. You take minus 2 down. Subtract 1. Okay, so this is 1 over x cubed, right? And there has to be a 2 somewhere. Okay, so here, 2 minuses kill each other. Okay, so everybody agrees this is the... So this is when x is different than 0. Okay, because the function is given with this formula only when x is different than 0. Okay, so we look at this. When is it equal to 0? Never, okay? Exponential is never 0. 2 over x cubed is never 0. Okay, so f prime x is never 0 if x is different than 0. Okay, so what do we do now when for the derivative at x equals 0? Okay, f prime 0 is equal to limit x goes to 0, f of x minus f of 0 over x. Here we need L'Hopital's rule, which we didn't do. Okay, so using L'Hopital's rule, which we will do later, we get that this is equal to 0. Okay, so let me skip that detail. Because you see here, f of 0 is 0, so you don't have this. F of x is this. I'm dividing this by x. Okay, so as x goes to 0, both of them are undefined. Both of them go to 0. So the whole thing is undefined. So you have 0 over 0. Okay, so with the methods we did so far, there is no way to remove this indeterminacy. Okay, so since this is a simple indeterminacy, you only have x in the denominator. You apply L'Hopital, and L'Hopital tells you that this thing is going to be 0. Okay, so this is this is our function. We have only one critical point. Okay, so 0 is the only critical point. So I calculate f of 0. It is given as 0. So this is the number. So the endpoints now. Okay. So endpoint situation is the same as in the previous problem because the endpoints are plus infinity and minus infinity. So I have to take the limit. Here x is given as x squared, so it doesn't matter whether I put minus infinity or plus infinity. So I look at limit as x goes to plus or minus infinite, f of x. Now, when x is going to plus infinity or minus infinity, obviously x is too far away from 0, so I have to use this formula. So limit x goes to plus or minus infinity e to the minus 1 over x squared. Okay, so what is this limit? What? You are not a 1 with a question mark? 1. Okay, so the limit is 1. Okay, so exponential is a continuous function. So continuous function means that the limit operation goes inside. That's how we define limit continuous function. Now you take the limit of minus 1 over x squared. So minus comes out. So you look at limit of 1 over x squared as x goes to infinity. That's 0. E to the 0 is 1. Okay? So the function never takes the value of 1. But f is never equal to 1. Okay, so because at 0 it is 0. When x is different than 0, this is the expression. E to the something will be equal to 1 only when that something is 0, but this something is never 0. Okay, in the limit it is 0, but it is never 0. So the function never takes 1. Okay, so we have a situation in the inverted picture of the previous problem. So the graph is something like this. Okay, so y, so this is 1, this is x, and the function is something like this. It touches here nicely and then goes. So it is symmetric with respect to the y-axis because plus or minus does not exist. Here, minimum. Now, the analysis of this thing is minimum of f is 0, max does not exist. And if you want to summarize this situation here, you say the supremum of f is 1. Okay, the function never takes the value 1, but 1 is significant. If suppose the function takes the value 1 somewhere, again you can say the supremum of f is 1 because maximum is also a supremum. When you say maximum, you claim that the function takes that value. When you say supremum, you don't make that claim, but you don't make any other claim either. You are not claiming that the function never takes this value. Okay, supremum is just you throw one of your claims. Okay, so this 1 is some significant number in this sense, but the function may or may not take it. You didn't want to check that, so then you use the word supremum. In this particular example, we check that the function does not take it. Okay, so let's see if I have something else to do before this. Those things I did last hour. Okay, so these are the things. I have a nice problem. Okay, let me do this problem quickly so that next hour we start with mean value theorem. Okay, so let me do this one. Okay, so another example. So what is the number? 7, 8. Okay, so 8. Our function is f of x is equal to 5 x to the power 2 over 3 minus 2 x to the power 5 over 3, and x is in the interval minus 1, 2. Now, if you want to plot this, this is the graph. So it comes down like this, and then it goes like this. Okay, so this is 2, this is minus 1. And at this point, we will have the tangent line horizontal. Okay, so let me quickly write these things. This is the graph. You see that maximum will occur here. Okay, minimum will occur here. And this is a critical point in the sense that the derivative does not exist here. This is a maximal point in the sense that it's an endpoint. Here we have a local maximum. The derivative is 0. That's a local maximum. At this point, we have a local minimum. It's an endpoint, but from the figure, we see that it's a local minimum. This number is smaller than the nearby points. Okay, so this is, if you plot the figure, this is what you see. Of course, you don't see that the local maximum occurs at 1. You calculate this one after the derivative. Okay, so let me quickly do this. Okay, so you take this down. This is 10 over 3 x to the power minus 1 over 3 minus, and the same thing here, 10 over 3 x to the power 2. Okay, so you simplify this as 10, 1 minus x over 3x 1 over 3. So this is the derivative. Okay, so you see that the derivative is not defined at x equals 0, and otherwise it is equal to 0 at x equals 1. These are the things that I'm interested in when I ask for the critical points. Okay, so f prime is not defined at x equals 0, and f prime is 0 at x equals 1. So these are critical points. Critical points. And I evaluate f here. F of 0 is 0. And f of 1 is, what is f of 1 here? F of 1 is 3, of course. Okay, so I put x equals 1 here. You get 3. Okay, so this is 3. I didn't write the y coordinates here. So these are the two numbers that I keep. Okay, then endpoints. F of minus 1 and f of 2. Okay, so let's see. F of minus 1 is 7. F of 2 is 4 to the power 1 over 3. So this is approximately 1.5 something. Okay, so these are the other numbers. So as I suspected from the figure, I have 4 significant numbers. The value of f at this point, at this point, at this point, and this point. Okay. So now looking at these numbers, so that's where calculus reduced this. Instead of examining all these points, I now examine only 4 points. Okay. So minimum of f is 0 at x equals 0. Maximum of f is 7 at x equals minus 1. So that's the conclusion. Okay, so this is again a typical problem on a closed and bounded interval. Point where the derivative does not exist proved to be important, and point proved to be important. Okay. Okay, so that's all. Let's take a break and then we'll continue.